Okay, worksheet 23 is a closer look at some common models. In each of these exercises, you'll be using the tools you've already learned, and what you're going to do is look at some of these prototypical models and say what happens when you change certain coefficients or constants like A or B or L in the models that you're seeing now. Okay, and also in question, the end of the last couple exercises, you're going back to more common things that you're used to seeing, like a parabola or whatnot, or maybe a quartic. So, for example, what I'm going to do in this video is I'm going to show you what the thing looks like in the simplest case, so you can get a sense for what it is you're being asked to do in these exercises. Okay, so in the first example, if I let A equals 0 and B equals 1, that would be the simplest case possible for this particular graph. And so you can just look at a couple prototypical examples and just get a sense for what's going on. You can see that this function has a max is at a pretty obvious place. And then there's going to be a point of inflection, wherever that is. Funny, that looks a little bit like negative 0.707 to me, but that's just me. Hint. But what you want to do if you're having trouble getting this started is take a really simple case, make the variables as simple as you can, plot it on Desmos or Wolfram Alpha, and then go and work out the calculus without any whistles and bells. Just double check and say, oh wait, I just determined that whatever this is where the point of inflection is, and then I look on my graph at Desmos and I say, okay, that looks like it's right. I did the problem correctly using a simplified model. Then you go back and answer the question as it was posed, where it says, okay, now put all those constants back in, and now generically in terms of A and B, see if you can find the max and the points of inflection and so forth. So the first model that we're looking at is the normal curve. Let me try to draw that. Okay, that's about as good as we're going to get. And the question is, what does A and what does B do? So one possible answer is maybe it shifts your curve this way. Maybe it does this sort of thing to your curve. Maybe it does this sort of thing to your curve. Maybe it makes it skinnier. Maybe what it does is it makes it narrower like this. Like narrow and tall maybe. But there's going to be some sort of shifting that happens to the shape based on A and B. And so it's your job to play with A and B and also use what you know about graph shifting so that you can answer those questions. Okay? And okay, so that's the end of that example. Let's ask about what the logistic curve does. Okay, so this is the logistics equation, and in this rendition of it we have an L, a capital A, and a K that we can control. And the point I want you to note is that this function has a location about which you have kind of a rotational symmetry. It might not be perfectly rotationally symmetric, I'll leave that to you to decide, but there's a limit, there's an upper limit, a long time behavior where it stabilizes, in this case at y equals 1, and left hand behavior it stabilizes at y equals 0. And there's this fun area in the middle where you transition between them. Okay, you might even consider the relationship between this curve and the bell curve in terms of, could one potentially look a lot like the derivative of the other? That's something to think about. But for this exercise, what you want to do is figure out what's going on. This particular example, we have right in the middle, we have a point of inflection, we have concave down on the upper half of the curve, and concave up on the lower half of the curve. So this curve has exactly one point of inflection and two horizontal asymptotes between which this curve lives forever. Okay, so that's the characteristic here. And again, what you want to do is you're thinking in terms of, let me try to sketch this thing. Again, it's not perfect, but it's okay. So there will be something that causes this guy to get steeper or narrower. So there's a way to control that. and there's a way to shift the whole thing right and left, and there's a way to make it grow kind of like that. Okay, that kind of thing. So those are the kind of shifts that we're trying to consider. And so your job is to play around with capital L, capital A, and K and see what things happen. And again, you should use your intuition and your knowledge of how we deal with these things anyway, generically. Like we already know about graph shifting from pre-calculus, but this is going to help sort of seal those concepts in. So you can kind of tear this function apart and see what's causing these coefficients to allow us that kind of control. Okay, so one more to look at generically. Okay, so this is your surge function, and the surge is referring to this portion, which in this graph is kind of near 1-ish. So notice there's this part below that where you're ramping up, and then there's kind of a hump, and then it levels down. So we have a concave down portion of the curve as it's increasing up to its max point. Then it's going to continue concave down for a little while and hit a point of inflection and concave up. So its increasing portion is going to be only concave down, and then if it's decreasing, it's concave down, and then it's going to hit a point of inflection and concave up. So that's the general overall look of this. But again, your job is to investigate the effects of changing A and B to figure out how you have control over the shape of this surge function. But I just wanted to point out the general features so you know what you're looking for, you know what you're trying to do, okay, what you're looking for. Okay, so hopefully that helps you understand what it is you're doing for the first few questions. And then you have the same kind of logic for the last two questions. Okay, I'm going to hide the function itself. I just want to show you, I'm showing you the curve, but I'm hiding the equation. So I wanted to show you in relation to question 5b, this is one way in which your function can look, depending on your choices for A and B. And here's another potential way your function can look. Notice in the first picture you had a max and a min, whereas here you don't have a max or min because the way this function splits. You still have an asymptote, but you're coming in, like on the left-hand side of the equation, you're just coming in one continuous direction, and then you do an asymptote, but you keep, like this entire function is decreasing. You could also adjust A and B so that this function is entirely increasing. So your job is to play with A and B so you can get these different effects on this prototypical type of shape and figure out what you do to A and B to control that. Okay, and just glancing over at your worksheet, I don't want to give away too many clues. I think I've given you enough hints, and that's enough, so you guys can go work on that and then come back to class with questions. Okay, have fun with those. I hope you do, because it's a lot of exploring, playing, and graphing on Desmos and Mathematica together, so you're trying to like merge the theory and the practice, and so I hope you have a lot of fun with this one.